You know, for centuries, we've tried to understand our sun by basically just staring at it from the outside. But to really crack its secrets, we have to go inside. So today, we're going to explore the sun's fiery interior, not with telescopes, but with some of the most powerful supercomputers on Earth. We're literally building a star from the ground up to finally understand its magnetic heart.
Okay, so what you're looking at here is the sun's magnetic activity over the last 50 years. It's often called the butterfly diagram, and you can see why, right? See those patterns? Sunspots pop up at the mid-latitudes and then kind of drift towards the equator, making these wing shapes over an 11-year cycle. It's incredibly regular. But, and this is the big but, the sun's interior is a chaotic, boiling sea of plasma. So how on earth does all that chaos create such a predictable, rhythmic pattern? That's the real mystery.
So how do we even begin to answer that? Well, we've got a huge problem. We can't just send a probe into the sun's core, obviously. The inside is totally hidden from us. So if we can't go to the sun, we have to bring the sun to us.
And this quote just lays it all out. It's the core challenge for every solar physicist. We can see the surface, sure. We can measure the light it gives off. But the engine driving everything, all the turbulent flows and magnetic fields deep down inside, it's a complete black box. We have all these theories, but no direct way to check if they're actually right.
So what's the solution? You build a virtual sun inside a supercomputer. It's that simple, and that incredibly complex. These three-dimensional simulations are basically our digital telescopes for looking inside a star. And in there, we have access to everything, every single flow, every magnetic field line, every little temperature change. It is the only way to see the whole picture and really put our ideas to the test.
But here's the thing. You don't just sit down and build a perfect digital star on your first try. It is way, way too complicated for that. Instead, scientists have this really clever step-by-step strategy. They start simple in a totally controlled environment and then build their way up to the real thing. It's a journey from a simple sandbox to a full-blown star. Step 1 is what we call a Class 1 simulation, and really, you should think of it like a scientific sandbox. You've got a simple, contained box where scientists can isolate just one tiny piece of the physics puzzle. For instance, they can use what's called forced turbulence to artificially create a very specific type of motion, like a helical corkscrew flow, and then just watch to see what exactly that one thing does to the magnetic field. It's a perfectly clean, totally controlled experiment.
Now, the next level up is the Class 2 simulation. Here, we're moving from that sandbox to taking a virtual core sample of the sun. It's still a local box, but now, instead of forcing the turbulence, scientists just let the physics run wild. They set up the basic conditions for convection, that roiling, boiling motion of hot plasma, and the complex turbulent flows just emerge on their own. It's a huge leap in realism, but remember, we're still just looking at a tiny slice of the star.
And that brings us to the final step. This is the ultimate goal, the holy grail, Class 3, the global simulation. The idea here is to model the entire star in its proper spherical shape and to capture the full complex dance between convection, rotation, and magnetism. These are, without a doubt, the most realistic and powerful models we can build. They're also breathtakingly expensive, demanding years of time on the world's absolute biggest supercomputers.
So let's just break that down real quick. The key thing to remember is this progression. We start at Class 1 with external forcing in a local box. We move up to Class 2 where physics runs itself but still in that local box, all the way to Class 3 where that self-consistent physics is now operating on a global, spherical scale. Each step adds a ton of realism but also a ton of complexity.
Okay, so we've got these incredibly detailed, complex digital suns. But how do we know they're actually telling us anything true about the real sun? How do we connect all this messy, chaotic simulation data back to our fundamental understanding of physics? How do we know we're not just fooling ourselves?
Well, this is where a really powerful idea called mean field theory comes into play. For decades, this has been the go-to framework for trying to explain the sun's magnetic cycle. It's basically a set of mathematical equations that averages out all the small-scale messy stuff, the turbulence, and just describes the evolution of the big, large-scale magnetic fields. You know, the ones that make that butterfly diagram.
But here's the catch. It's a simplification, right? A theoretical shortcut. And for years, we couldn't be totally sure if the assumptions it makes were actually correct. But now, we can check.
These big 3D simulations with all their chaotic detail, they provide the perfect ground truth. We can take the raw data from a big, messy Class 3 simulation and see if the elegant, simplified rules of mean field theory can actually predict what's going on. It is the ultimate validation test. And the results are just stunning. Seriously. On the bottom, that's the messy reality, the averaged magnetic field taken straight from a global 3D simulation. On top, that's the clean version, the one reconstructed using only the simple math of mean field theory. I mean, look at that. The match is incredible. This is the aha moment. This gives scientists real confidence that the theory is actually getting the essential physics right.
So this validation is a huge win. It proves our basic physical understanding is on the right track. But it also raises a really critical question. If our theory works inside our simulated sun, how well does our simulation actually match the real sun? And that leads us to the big reality check, what we call the computational chasm between our digital star and the genuine article.
Yeah, one of the biggest head-scratchers right now is something called the convective conundrum. By studying sound waves traveling through the sun, we know that the large-scale convective flows are actually much slower and calmer than even our best, most advanced simulations predict. It's a huge puzzle, and it tells us that our models are still missing some fundamental piece of the physics.
And just to give you a sense of the scale of this challenge, let's talk about turbulence. A key number that describes it, called the Reynolds number, is around 10 to the power of 12 in the sun. That's a 1 with 12 zeros after it. Our best simulations today, they can barely manage a few hundred. We are orders and orders and orders of magnitude away from reaching true solar conditions.
These limitations create some really stark contrasts. The real sun has a mind-boggling range of physical scales, from tiny swirls to flows the size of continents, all happening at once. Our simulations are limited by computer memory. The sun's plasma is incredibly fluid. It's actually thinner than water. But to keep our simulations stable, we have to make the plasma artificially viscous, often as thick as honey. And to watch just one 22-year magnetic cycle play out, that can take years of real-world time on one of the biggest supercomputers in the world. We're getting closer, but we're definitely still simulating a slightly different, much simpler star.
So, with all these massive challenges, how does any of this push science forward? How do we actually use this to crack the solar code?
Well, it all comes back to that brilliant strategy. We use these different classes of digital experiments, and each one has a very specific job. The simple sandbox models, they help us isolate and really understand the basic rules. Then the big global simulations test those rules in a much more realistic, chaotic environment. And by using those simulations to validate our theories, we build real confidence in what we know. Each step, from the sandbox to the star, gets us one step closer to finally deciphering our sun's magnetic heart.
Look, the gap between our simulations and the real sun is still vast, but is shrinking with every single new generation of supercomputers. Our digital suns are getting more powerful and more realistic every single year. So the question isn't really if they'll unlock the sun's remaining secrets, but when. And what do you think they'll reveal next?